Okay, good morning, good evening, good afternoon, everybody, wherever you are in the world. Thank you so much for joining for the workshop. Yeah, as Henrik mentioned, my name is Xerxes. I'm the product manager for the Waymo Open Dataset project. I work closely with applied research more broadly within Waymo, and I'm really excited. I count it my extreme privilege to be able to be here today and talk about the Open Dataset challenges, to officially announce the winners. We're really excited about that, and let's get right into it. I won't take too much time. But before we start talking about the challenges themselves, I just want to kind of give a recap of the Waymo Open Dataset as it is today for those who may not have been familiar with it. So right now we have nearly 2,000 scenes of 20 seconds at 10 hertz. And we have 5 LiDARs and 5 high-resolution cameras that feed into the data with very high-quality synchronization between them. Obviously, we have the calibrations and vehicle poses as well. And we have a lot of high quality labels, so more than 11 million 2D labels in 1,000 of the segments, and more than 12 million 3D labels in 1,200 segments. So not all the segments are labeled. We have some in the test set, the labels are held back. We have other segments that we released unlabeled to try different sort of unsupervised techniques, but this is what we have as of right now. We first launched the dataset version 1 back in August of last year. And we were really happy to do that. It was the first time we had done something like this. And at the time, we said, we want to continue to grow the data set over time. And we have tried to keep that promise. So we had some further releases, a smaller release in February. In March, we released the test set, again, with labels held back. And we also released a domain adaptation set too. So the idea behind that was to basically release a different test set from a different domain, particularly a different geographical area, as well as different predominant weather, which was largely, we also released training and validation sets, which were largely unlabeled. But the idea was to see how well models could adapt to this other domain. And we're not done yet. We're hoping to continue to grow the data set, both in terms of the number of segments, as well as the types of tasks that you can do with it. So please stay tuned for more details for that in the near future. So let's talk about the challenges. So we had 5 that we launched with, and again, we would like to do more of this, particularly considering the response that we had, and we'll talk about that in just a minute. But the 5 challenges we launched with were 3D detection and tracking, 2D detection and tracking, and domain adaptation, which was basically 3D detection, but with that different domain that I mentioned, and exactly what that was, it was Kirkland and mostly in the rain. So we were really pleased with the engagement that we saw here. So we launched the challenges March 19th, and we closed them, at least for the purposes of this workshop and for the purposes of awards, on May 31st. And we had admittedly a little bit of a slow start on the leaderboards, but towards the end, it really ramped up and it exploded towards the end of May, and we were really happy to see that. So in total, we had 165 teams that participated in some capacity. So again, if you're not familiar with the way the challenges were structured, we had both a test set and a validation set running on that eval server on the website. So you could upload your results for testing against the validation set or the test set or both. And 165 teams did something. So contributed some results against one of those. You were not required to post your results to the leaderboard, but we had 100 unique methods that were posted to the leaderboard publicly, which, by the way, are still open. And we do intend to keep them open for the foreseeable future, so you can continue to try out new methods, challenge the positions in the first few, first top 5 or top 10. We would love to see how things progress over time there. So we had 100 unique methods on the leaderboards, which we're really pleased to see across the 5 challenges, and over 2,000 evaluations against the validation sets. So we were limiting how many times people could validate against the test set, but against the validation sets, it was unlimited, and we're excited to see more than 2,000 submissions against that. So I just want to pause really briefly and say thank you. I know many of the people who contributed something to the leaderboard and participated are probably listening right now. So a huge thank you to all of you. You're the ones that made this a success. I keep saying this, but it's true that we are really pleased with the result, both in terms of quantity and quality. And thanks to your hard work, we will probably do something like this again in the future because we see that it was well received. And again, thanks to all of you. So let's now talk about the winners. Again, the leaderboards are all public. You can see them on waymo.com/open, but let's make it official right now. So here we go. So the first challenge for 3D detection. In first place, we have the method Horizon LiDAR 3D from the team from Horizon Robotics. So excellent work. Again, if you do want to look into these methods, the metrics and the statistics and the PR curves and everything, you can go to waymo.com/open. The leaderboards are all there. You can click through on entries and get the detailed statistics. And we are, of course, going to hear from these folks in just a few minutes. So a lot more details to come, but for now, these are the standings. In second place, PV-RCNN from the team from the Chinese University of Hong Kong and the University of Hong Kong. And in third place, TS LiDAR Det from a team from TuSimple. So fantastic work, all three teams. Again, thank you so much for participation. You deserve to be in these 3 spots. All right, 3D tracking. In first place, again, we have the team from Horizon Robotics. Kudos to you all. In second place, again, the team from the Chinese University of Hong Kong and the University of Hong Kong. Fantastic. And third place, we have a team of 1, Almaz from BTS Digital, probabilistic 3D mod. So big kudos to all of you as well. Congratulations for the first 3 spots in 3D tracking. Okay, 2D tracking. In first place, we have a team from TuSimple and their partner universities. Fantastic. Second place, we have Horizon Robotics. And in third place, we have a team from Sun Yat-sen University and Huawei Noah's Ark Lab. So again, congratulations to all of you guys for 2D detection. 2D tracking. In first place, Horizon Robotics. Second place, method Quasi-Dense from a team from UC Berkeley. And in third place, we have a team from the Technical University of Berlin. So kudos to all of you guys for the 2D tracking top 3 spots. And lastly, domain adaptation, which again was essentially 3D tracking, but to see how well that could adapt to a different domain. The test set was from a different domain and only a fraction of new training and validation data were provided. So in this case, first place again, the team from Horizon Robotics, which is now 4 out of the 5 challenges they got first place in. So tremendous accomplishment. Thank you for participation. And in second place, also multiple challenges in second place, the team from the Chinese University of Hong Kong and the University of Hong Kong, fantastic work. And in third place, simple baseline V2 from a team from Innova. So this is fantastic to see. We had several teams placed in many of the challenges, which is great. I, for one, am looking forward to hearing from these teams in the next few sections. So I'm going to try to wrap it up now. And I'll just say congratulations again to everyone who participated. Again, we're super pleased. We're super appreciative of the time and effort you put into this. We know it was not easy. A lot of these techniques just really, really high quality. And so I'm gonna stop talking now so that we can give our attention to the folks who can present some of these methods and talk about how hard they worked on these challenges. So I'll stop here. I'll hand it back over to Henrik.
Thank you. I hear that our first presenters are ready for the presentation, so I'm going to hand it over to them.
Okay, good morning, everyone. So my name is Wang. I'm the lead of the Team Horizon. Today, I'm very excited to be here to present our solutions for the Waymo challenges. So our solutions eventually reached the first place in 4 of the 5 tracks and second place in 1 of the 5 tracks. So I want to take this opportunity to thank the Waymo organizers for organizing this amazing challenge and also for giving us this opportunity to share our solutions with the public. So here's the outline of today's talk. First, I'm going to introduce Team Horizon, then I will give an overview, and also I will share some of my own thoughts with everyone. Before I dive into the details of our winning solutions, I divided our solutions to 3 groups: the 3D detection and the domain adaptation, 2D detection, and finally the 2D and the 3D object tracking. So here's a slide showing all the team members. As you can see, yeah, most of them are pretty young. They are just graduated from school, but they're very talented. They are probably the most talented engineers that I have ever worked with. So it's because of the teamwork, because of the close collaboration between the teams that helped us win this challenge. So for those of you who don't know Horizon Robotics, we were founded back in 2015. We are a pioneer and a global leader in developing software and hardware edge AI solutions. So we have a strategic focus on ADAS, autonomous driving, and also in-cabin artificial intelligence. Some of you might know our CEO, Caillou, because he won the 2010 ImageNet Challenge. That's way before the deep learning era. And he was the founder and head of the Baidu Institute of Deep Learning. On the right is an image showing our booth in the CES 2020. So this year we have 4 CVPR main conference papers authored by our interns accepted. I listed their names here. And also I put a link to their PDF, and 3 of them open sourced their code. They released the code to open source community. So please feel free to check them out and come to their posters and talk to them. So I'm very proud of these interns. So one thing to notice is that the third paper was authored by Jialian Wu, who is currently my summer intern. And also another thing to notice is that the author of the OrgFPN, Shaoshuai, did a 2-year internship in Horizon Robotics, did a lot of amazing work, but he's now with the CUHK Lab, who also participated in this Waymo challenge. So just a shout out to our interns. So they did a lot of amazing work in Horizon Robotics. So before I dive into the details, I want to share some of my own thoughts about the challenges. First of all, I think Waymo Open Dataset is amazing because it enables a lot of new exciting researches. Finally, we can move away from outdated and sometimes even misleading benchmarks. So these older benchmarks served their purpose, but now it's time to move on to some real and larger scale dataset like Waymo Open Dataset. I think the annotations of Waymo Open Dataset are very accurate, and they are very exhaustive in the sense that every object in the image was labeled. But however, we did notice some annotation errors, as we will point out later in later slides. And personally, I think adding some computation constraints, or at least taking into account both accuracy and the speed, would make the challenges even more interesting. Also, personally, I was wishing for a track for monocular 3D object detection, because I think it's perhaps the most challenging problem in computer vision, because imagine that you have to infer the 3D location of an object just based on a single monocular image. That's very challenging. So finally, I would suggest a competition format such as the public plus private leaderboard used by Cargo, because I think it would encourage more people to share and publish their result on the final leaderboards. So my impression is that most people choose not to publish their result if they saw that they cannot make it to top 3, so which makes the leaderboard a little less interesting. So just some of my own thoughts. So before I dive into the details of our solutions, I want to show you an amazing video that we prepared for the 3D object detection and tracking. I'm not sure if there's latency if I play this video over Zoom, but let's find out. So as you can see, on the left is the bird's eye view image. On the right is a 3D view of the tracking result. Every object is being tracked. That's why they are displayed in a unique color, and also a unique ID is assigned to each object. So our tracker can track a large object like a bus, and we can also track small object like pedestrians. I'm not sure if there's any latency, but hopefully later we may upload this to YouTube so everyone can check it out. Yeah, here's my favorite part, because there are so many pedestrians and we still can track them. So this is really impressive. Actually, personally, I can just sit there and watch this demo all day long because it's so satisfying and so impressive. All right, so let me dive into the details of our winning solutions. Here's a summary of our winning solutions, and I summarized all the key aspects of each solution. For 3D detection and domain adaptation, we developed a very strong baseline named AF Detect. It's one-stage anchor-free and AMS-free. It's simple but elegant and effective. So we leverage camera information to enhance the point cloud. During training, we perform data augmentation, and during inference, we do test time augmentation, just like everyone else does. And for 2D detection, the key is to combine a one-stage and a two-stage detector. And we fine-tuned some expert model to handle the imbalanced data problem. And we employed the auto-ensembling to merge several groups of detections into the final result. For 2D and 3D tracking, so we developed an online unified tracking by detection framework for both 2D tracking in the image space and 3D tracking in the world space. Also, we defined some simple but pragmatic data association approach. So for the 3D object detection, we have developed a one-stage anchor-free LiDAR 3D detector named AF Detect. We use densification, temporal densification to enhance the point cloud. We also employ the pointer painting to further enhance the point cloud. During training, we do data augmentation. During inference, we perform TTA and ensemble. Finally, I'm going to show you the results and some ablation studies. So the AF detector is a one-stage anchor-free and MS-free detector. So which means there's no hassle with hand engineering or learning the anchors or whatsoever. So actually we have a CVPR workshop paper accepted. So please come to our poster this afternoon and talk to the team. So this is how it works. Starting from the point cloud, we encode the point cloud to a top-down view, bird's eye view pseudo image. And the final predictions include 5 heads. The one head for predicting a heat map, indicating the 2D location of the object, one for offset, one for z-value, another for the 3D dimensions, and finally a head for regressing the orientation. So we decode based on the 5 heads, the predictions to generate the final 3D bounding box. So the first step is to encode the point cloud. We use a standard voxelization, which produces a 3D volumetric grid based on the original point cloud. It's fed to a 3D feature extractor. And the resulting feature map will be reshaped to form the final pseudo image, which is a top-down view and a bird's eye view image. So under the AF detector framework, we used 3 networks. So each network takes the pseudo image produced by the point cloud encoding step. And as you can see from the networks, that we concatenate features from different levels to form stronger feature representation of the point cloud. And you may note that we actually use BiFPN in the B3 network. The block is repeated 4 times. We want to enhance the point cloud by leveraging temporal information and camera information. We actually merge all the points cloud of all the LiDARs to form the original point cloud, but they're still kind of sparse. So we do temporal densification. So we merge the point cloud of the current frame with the previous 4 frames to form a denser representation of the point cloud. We also use pointer painting. Specifically, we do 2D box painting and segmentation painting, which is about adding more attributes to each point. I will talk about the details in later slides. But please note that because Waymo does not provide real view cameras, it does not have a 360-degree coverage. So in the end, there might be only 50% of the points painted. So it's not 100%. Just to provide more details about the densification, we first transformed the point cloud from all the previous 4 frames to the global coordinated system, and then transform them to vehicle coordinated system, in which they will be merged with point clouds from the current frame to form the final densified frame. The right image shows an example. As you can see that for some moving object like a vehicle and a pedestrian, they actually have a long tail. You might argue that this might hurt the detection performance, but actually we believe it's beneficial for the estimation of the orientation of the object. So to give you more details about the point cloud enhancement, we inspired by the point painting, we do enhance the point cloud by adding more attributes to it. This is how it works. We project each LiDAR points to the camera view and gather some image information, 2D detection information, and a segmentation label, and append these features to the original attributes. Originally, each point has 4 values, X, Y, Z, and the reflectance, and we add more information to these attributes. So to form the final enhanced point cloud, it's a still point cloud, except that each point has more attributes. So we did an ablation study to study the breakdown of the improvements introduced by point cloud augmentation. We used the B1 network. It was trained on 5% of the training set and tested on 10% of the validation set. So the reason is we use a subset is because that we want to quickly verify the ideas, and also because we participated in all the 5 challenges. So our computational resources was a stretched thing. So that's why we choose a subset. But actually later we noticed that the result on the 10% of the validation subset is actually very close to the entire validation set. As you can see from this plot, that the densification introduced about a 5% improvement. 2D box painting further boosted the performance by about 2.5%, and the segmentation painting further improved the performance a little bit. So during training, we employ standard instance level augmentation to produce more ground truth, to produce more training samples. And we also use frame level augmentation to produce more training frames. During testing, we employ the test time augmentation. For example, we rotate the point cloud around the y-axis, the pitch axis, perform detection, and then rotate the detection back. So we argue that this is helpful for some scenarios, for example, slope, or if the camera has, or if the LiDAR has a pitch motion, in which some objects might be out of the detection range. So this is helpful to handle these cases. So the TTA produces multiple groups of detections, how to merge different groups of detections into the final result. We adapted the original 2D WBF weighted boxes fusion to a 3D version. So what it does is that it calculates the weighted average of the overlapping bounding boxes to form the final bounding box. It also assigns a new score to the final bounding box. And the bottom image shows one example of a 3D WBF. You can see the bounding boxes before and after the applying 3D WBF. So we also did an ablation study for ensembling. You can, again, it's also done in a subset. And you can clearly tell the contributions made by the benefits of combining different networks. For example, B1, by combining B1, B2, and B3, we can reach a MAPH of 8.9 MAPH-L2. And by applying TTA and the WBF, we can further improve the performance. And finally, we automatically search the parameters of WBF. That will give you another 1.5% boost. So now I will show you the final result on the 3D detection and the domain adaptation tracks. We reached the first place on both tracks, and we actually won by a big margin on the domain adaptation. I think the reasons are twofold. First, it demonstrates the benefits of using anchor-free and one-stage detector, because it has better capability of generalizing to another domain. It's robust to domain diversity. Another reason is that we use camera information, which makes our solution more robust to domain diversity. But as you may notice that there's still a domain gap. So which means our detector on the domain adaptation is still not as good as the 3D object detection, especially for vehicle and pedestrian. So that's it. In the future, we might further bridge this gap. So that was for 3D object detection. Now let me talk about the 2D object detection solution. We reached the second place for this solution. Our key is to ensemble a one-stage and a two-stage detectors. We fine-tuned some expert models to handle the imbalanced data problem. We used the label smoothing to handle some annotation errors. And as everyone else does, we use multi-scale testing. We also employed the ADJ software NMS and the WBF for merging the boxes. And also to better ensemble different groups of detections, we modified the original auto ensemble method to a greedy version. So as I mentioned, our final solution was produced by a one-stage CenterNet with our glass 104 as the backbone and a two-stage cascade RCN detector with the ResNex 101 as the backbone. So we believe they are complementary to each other. And yeah, we fine-tuned some expert models on top of the original main model to handle the imbalanced data problem. Specifically, we trained a dedicated cyclist pedestrian detector. We also trained a detector just for nighttime detection, another one just for daytime detection. So as you may notice from this image that some pedestrians were not labeled and some ground truths are very difficult in the sense that they are mostly, maybe 90% occluded. So to be able to handle these difficult samples, we actually perform label smoothing. And in multi-scale testing, we used 5 scales for CenterNet and 3 scales for the Cascade RCN. Yeah, by the way, Cascade RCN may be the predominant detector because I saw a lot of participants use Cascade RCN, but I didn't see anyone else use CenterNet. So yeah, so we didn't use the naive NMS. We used the ADJ soft NMS, which was developed by the first place solution for the Open Image Challenge 2019. But we made a slight modification. Basically, we added the first step. So the idea is illustrated here. For this vehicle, we want to suppress the redundant bounding box with a score of 0.7 and 0.5, but we don't want to affect the other vehicle by this vehicle. So the first step is to keep the other vehicle, and the second step is to remove the vehicle with a score of 0.7 using AMS. And the third step is to suppress the score of the vehicle with a score of 0.5. So after suppression, its score becomes 0.0 or 0.1 actually. So we also use weighted boxes fusion in CenterNet. So the idea is to perform to calculate the weighted average of the overlapping bounding boxes and also assign a new score to the final bounding box. So to best merge different groups of detections into the final result, we adopted the auto-ensembling approach, which was again developed by the first place solution for the Open Image 2019. So the idea is that starting from step 1, we started with our N detection groups. We merge each 2 groups into 1 group of detection. And for the merging operation, we select from a group of 5 candidates. And in the next step, we will further merge each 2 groups into 1. And in the last step, we merge the final 2 detection groups into the final result. All right, so we did an operation study again on the 5% of the validation subset just to quickly verify some ideas. As you can see, the greedy auto ensemble and the expert model gives boosted the performance by 2.3%. And by adding the CenterNet, the performance can be further improved by 3%. So actually, one of my impressions is that the final test set is actually easier than the validation set. I guess that's probably true for all the tracks. So the final leaderboard result, we reached the 2nd place, and the TuSimple approach reached the AP L2 of 74.4, which was very impressive. So that was for 2D object detection. I want to share with you our 2D and 3D tracking method. Actually, our method is not that fancy, but it's simple, intuitive, and also it's pragmatic. So we developed an online and a unified 2D and a 3D tracking by detection framework with following components. They're pretty standard. So we use 2D detection and real ID networks. We define some metrics for measuring the distance and the similarities. And also we proposed a novel 3-stage data association between 2D tracks and 2D, 3D tracks and the detections. We also have a component for track management, and we use common filter for state prediction and updating. Here's one example showing 2D multi-object tracking at nighttime. So there are many objects, many pedestrians, and it's a very crowded scene. On the right, I showed the 2 images. They are just screenshots of the demos that I just played. From the images, you can tell the complexity of these frames and how good is our tracking and the detection. So because our method is tracking by detection, so we have to use network to produce tracking detection first. Actually, at first, we modified the CenterNet for joint detection and the real ID feature extraction. The idea is to add a separate embedding head for extracting feature embeddings. And we also added a second stage for extracting the real ID features for each bounding box. It was still ongoing. We didn't finish it by the deadline, but it's still ongoing. So eventually we use CenterNet just for providing the detections, and we opted to train a small independent real ID network. It was trained from scratch on Waymo. And as for the 3D detection, we used detectors from our 3D detection track to provide the 3D detections. So here's an example illustrating the benefit of using real ID features. It's used to complement overlap metrics, which might fail on many occasions. For example, long-term occlusion or large displacement of the objects. For example, if there's a bump on the ground, there might be a big pitch motion of the camera, so which causes large displacement of the bounding boxes of the same object at consecutive frames. So here's one example. I highlighted 2 pedestrians using the arrows. They crisscross each other in a very crowded scene. But after the quick crossing and after several frames, they can still maintain their ID. So this is a very complex scenario. So how to calculate the distance or the similarity metrics between 2D or 3D bounding boxes? One set of metrics is based on the bounding boxes. We may use 2D overlap between axis aligned bounding boxes. We can also use rotated 2D overlap in the bird's eye view image. For 3D, we may use 3D IOU overlap, or alternatively, you may transform the 3D bounding box to the image space and calculate that 2D overlap instead. Actually, in our 3D tracking, we use 3D center distance. We calculated the Euclidean distance between 3D centers and then apply a Gaussian kernel. Alternatively, you may use Mahalanobis distance, which takes into account the uncertainty of the state. It uses the covariance matrix, but eventually find out that the Gaussian distance is the simplest, and it's actually also works better than the other metrics based on our experiments. So another group of distance metrics is based on the appearance. As I mentioned, we use RealD network to compute the feature embedding from each object. And then we use cosine distance to calculate the similarity between the feature embedding vectors. So we proposed a very intuitive, simple 3-stage data association approach. We started by dividing the detections to 2 groups. The primary set, which has higher scores, a secondary set, which has lower detection scores. And also we assign a unique a number to each track, which indicates its age. Age is the time since the last successful update, or the number of frames since the last update. And at the first stage, the matching is between the tracks and the primary detections. We start from the track with the smallest age and then iterate over through each track of increasing age and then solve a linear assignment problem. At the second stage, the matching is between unmatched tracks and the remaining detections from the primary set. We may use a different association metrics here, or we may use the same metrics but with relaxed conditions. At the final stage, the remaining unmatched tracks is between, the matching is between remaining unmatched tracks and the detections from the secondary group. Here's a simple illustration. We have 3 tracks, 4 detections. For track A, we predict its common state at frame T. The current frame, it's matched with the detection, so we update its common state. For track 2, it's unmatched. It does not match with any detection, so we increase its age by 1. If its age is larger than specified value, we might delete it. And for track 3, it's matched to a detection from the secondary set. So it's matched in the third stage. We also update its common state. For detection 2, its detection score is pretty low, so we treat it as a false net positive and don't do anything about it. For detection 3, it has a very high score, 0.95. So, but it's not matched with any track, so we initiate a new track based on this detection. So as you can tell, as you can see, that is pretty simple, intuitive. So we always believe that the best algorithm is always the most elegant one. So specifically for 2D tracking, we track each class, pedestrian, cyclist, and vehicle separately, and also we treat each camera differently by specifying different set of parameters. We use ReID features in the first stage, and we use 2D overlap in the second at the third stage. To exclude unlikely associations, we specified some appearance and overlap thresholds. As for common filter, the state space is 8-dimensional vector. Observation is just a 2D detection with a detection score. The same for 3D tracking, we track each class separately. And Gaussian distance was used throughout all the three stages. Based on our experiments on the validation set, we found that Gaussian distance is actually not only faster, but better than Mahalanobis distance, and also better and faster than 3D and BEV IOU distance. To exclude unlikely associations, we also specify distance thresholds. As for common filter, the state space is a 10-dimensional state vector. The observation is the 3D detection, which is defined by 3D location, 3D dimension, the heading, and the 3D detection score. So we did an ablation study to study the contributions, the benefit of introducing third stage association and adding the ReID model. As you can see from this table, by introducing the third stage association, the performance can be boosted for about more than 6.3%. And by adding the ReID model, the performance can be further boosted by another 2.5%. So the last slide shows our final standing on both 2D tracking and 3D tracking leaderboards. We reached the highest MOTA L2, and also we have the lowest miss rate. So as you can see that we are actually very close to the second place on the 2D tracking leaderboard. On the 3D tracking leaderboard, we also have the lowest false positive and mismatch. So this concludes my talk, and thank you very much. I want to thank again the organizers for organizing this amazing challenge. So now I think I will take some questions. Thank you very much.
Okay, next up is a set of presentations of the winners of the Waymo Open Dataset. And the first presentation is actually going to be a recording, and we're gonna watch that now.
Hello everyone. First, thank you for the invitation from the Waymo Open Dataset team. My name is Shaoshuai. and currently I am a PhD student from the Multimedia Laboratory of Chinese University of Hong Kong, and I am supervised by Professor Xiaogang Wang and Professor Hongsheng Li. Here I present the PVRCN framework, the top-performing light-only solutions for 3D detection, 3D tracking, and domain adaptation 3 checks of the Waymo Open Dataset challenges. As we know, previous 3D detection methods generally adopted 2 strategies for point cloud feature learning, and they each have their advantages. The first one is the point-based set abstraction operation proposed in PointNet++, which has flexible receptive field and remains accurate point location. The other one is the voxel-based sparse convolution, which is more efficient and could also generate high-quality 3D proposals. Then, how to combine them and take the advantages from both of them in a single 3D detection network is what we would like to do next. To solve this problem, we designed the key point scheme to deeply integrate the point-based and voxel-based 2 strategies in a single 3D detection framework, which could take the advantages from these 2 strategies and effectively improve the structural diversity of our detection network to further boost the 3D detection performance. Our proposed PVRCN framework is a 2-stage 3D detection framework, which consists of the voxel-to keypoint scene encoding stage and the keypoint-to-grid R feature abstraction stage. In the first stage, we use 3D voxel scene with sparse convolution for efficient multi-skill feature encoding, and that is naturally combined with the anchor-based scheme to generate high-quality 3D proposals. Then, a small set of key points are sampled from the raw point cloud for encoding the whole scene, which remains accurate point locations for the following fine-grained RI refinement. For encoding the whole scene to the key point features, we propose the voxel set abstraction module to incorporate the point features and the multi-skill voxel features into a small set of key points. For the feature encoding of each skill, the strategy is that we keep each key point as a ball center with specific radius for this skill, and then we group the sparse voxel-wise features to key point features via point-based set abstraction within each ball. In this process, the voxel features are aggregated with point-based set abstraction strategy, which established the process of point-voxel feature combination. Then, the aggregated point voxel features from multiple skills of the backbone are combined as the final key point features. The generated point-wise key point features encode both accurate location information and the multi-skill semantic information, which is helpful for the following fine-grained proposal refinement. Since in the following proposal refinement network, the foreground key points should contribute more, while the background key points should contribute less, so we also propose the predicted key point weighting module to reweight the key point features with extra supervision from foreground key point segmentation, where we utilize the predicted foreground confidence to reweight the key point features. In the next key point to grid R feature abstraction stage, to group the key point features for proposal refinement, we propose the R grid pooling strategy. In contrast to the VSA module of last stage, here the R grid points are set as ball centers to group the surrounding key point features with multiple radius by the set abstraction. By this strategy, the receptive field of each grid point could even beyond the 3D RI boundary to aggregate the features of nearby foreground points, which are not inside the 3D proposal due to inaccurate 3D proposal generation. Furthermore, compared with previous pooling strategy like R-aware pooling, or proposed R-grid pooling could generate denser, sparse voxel-wise features, since the key point features could be utilized to multiple grid points, and this denser representation is benefit for encoding more effective proposal features for the following proposal refinement. Finally, we will reassign the R-grid features to a single feature vector, and then use fully connected layers for the final proposal confidence prediction and box refinement. During the computation, we also developed several variants of PVRCN as shown here. Our previous object classification is conducted in the RPN stage, and the second stage only estimates the confidence of each proposal. At this variant of version 2 PVRSN, the RPN only generates class-agnostic proposals, and we conduct the classification in the second stage. Our experiments show that with more accurate RI features for classification, this variant could achieve higher performance on pedestrian and cyclist, while achieving a bit lower performance on the vehicle category. These variants of PVRSN are finally utilized in the model ensemble process. We first reported the PVRSN results on our CVPR paper, where we could see that our method outperformed previous state-of-the-art methods with large margins on all levels and all distances. And there is also a video visualization of our detection results on the Waymo open dataset. For the Waymo challenges, actually the most important check is the 3D detection, and both the 3D tracking and domain adaptation performance are relied on the 3D detection results. So we mainly focused on improving the 3D detection performance based on our proposed PVRSN. We start with the vanilla PVRSN trained with half data from Waymo open dataset, which already achieved a relative high performance. Then we incorporate the last frame to simply concact with current frame for getting a denser point cloud, which leads to a small improvement. Next, we adopt the dynamic voxelization in the testing stage, and the performance also improved a little. Then we trained the PVRSN with 4 Waymo data and more epochs. The performance improved significantly at this time. Then the soft NMS was adopted, which further improved the performance. Then we conducted the model ensemble on several variants of PVRSN with small modifications, and the performance was further improved. By using only point cloud as input, our proposed method finally achieved first place among all light-only methods, and second place among all multimodal methods in the Waymo 3D detection challenge. For the 3D tracking challenge, thanks to our powerful PVRSN 3D detection framework, we simply utilize the Kalman filter-based tracker on our 3D detection results, which already achieved powerful performance. And our method finally ranked first place among all light-only methods, and second place among all multimodal methods on the Waymo 3D tracking challenge. For the domain adaptation challenge, we also conducted a simple strategy by fine-tuning our 3D detection PVRSN model on a small set of labeled data from target domain, except that for the testing of cyclist category, we directly utilized the source PVRSN model since there are very few cyclists in the labeled data of target domain. And this simple fine-tuning based strategy already achieved really good results on the testing set of target domain. And our method also ranked first place among all light-only methods, and second place among all multimodal methods in the Waymo Domain Adaptation Challenge. Finally, I would like to introduce our 3D object detection toolbox, PCDAT, to you, which I released 3 months ago and hope to help more researchers to be easier on conducting 3D detection experiments. And we are upgrading PCDAT now and are going to support more models and more datasets on PCDAT, which will also be released recently. And our PVRSN codes will also be added to PCDAT soon. Welcome to try, start, and contribute to the PCDAT codebase. Thanks for watching, and feel free to contact me for any questions.
Since this was a recording, we're not going to take live questions now, but feel free to ask your questions on Slack, and the authors are going to get to them later. Okay, next up is Wang from TuSimple to present on their results in the Waymo Open Dataset Challenge.
Okay. Hello, everyone. This is Zehao Huang from TuSimple. Today, I will introduce our solution for the Waymo Open Dataset Challenge 2D Object Detection Track. This work is done with Zehao Chen, Qiaofei Li, Hongkai Zhang, and Naiyan Wang. We will first analyze the scale distribution of objects in Waymo Open Dataset, and then, based on our analysis, we show how we conduct our baseline framework. Finally, we will show the experiments with pairs results and our final submission result. Okay, here we visualize several images from WOD and CUHK respectively. As you can see, the difference of object scale between these two datasets is very huge. Comparing to CUHK dataset, there are many small objects in WOD. Then we compare the scale distribution of objects in WOD and CUHK dataset. The X9 of this finger is the scale of bounding box relative to the image. The Y9 is the fraction of bounding box in the dataset. The blue curve is CUHK and the brown one is WOD, as shown in this figure. The relative scale of objects in WOD is about 3 times smaller than CUHK. Okay. Detecting very small objects is a challenging problem in 2D object detection task. In our solution, we adopt 3 strategies to address this issue. The first is feature parameter network. The second is large resolution image, and the third is scale-aware test. For baseline framework, we adopt feature parameter network. Based on our analysis of scale distribution, we adjust the anchor scales in RPN and the ROI assignment strategy in RCN. The anchor scales is about 3 times smaller than the original FPN setting. For RCN, we replace the ROI area from 224 to 76. Here are the detailed setting of our baseline experiment. We adopt ResNet 50, FPN, and SyncBN. In baseline, we use small scale images for both training and test. HGG with cosine linear rate schedule is used for training. The linear rate is set to 0.08 and the best side is 64. The whole training cost about 90 hours with 32 GPUs. Here are the results. Our baseline achieved about 50 MAP in validation set and 53.6 in test set. Then we will introduce our experiments with pairs and results. Okay, the first trick is large scale images. We adopt multi-scale training with random crop and large scale image for test to improve the performance of small objects. Multi-scale training and large-scale test achieve about 60.4 MAP, which is 10 points higher than the baseline result. Furthermore, we adopt cascade RCN to get high-quality results. We also use double head and PANet to get for better performance. During training, we do not append ground truth into proposals, and we only use 1,000 proposals for RCN. Then we use more scales for multi-scale training. This strong data augmentation achieves large improvement for cyclists, since the training samples of cyclists is much less than the vehicle and pedestrian. Oh, sorry. During test, we found our model tend to predict overconfidence classification scores on Waymo Open Dataset. The score of many predictions are nearly 1.0. To optimize for AP, we calibrated the classification scores by adopting a temperature T to produce a softer score distribution over class. These tricks achieved about 66.8 performance in validation set. For better performance, we adopt scale-aware test. We use 2 different resolutions for multi-scale test. The small resolution is used to get large objects. The large one is used for small objects. So scale-aware test bring about 2.1 improvement. Comparing to vanilla multi-scale testing, this simple strategy can achieve about 1 point higher performance. Finally, we adjust NMS threshold for different class and adopt bounding box voting. ResNet, Res2Net, ResNest, and HRNet are used for ensemble. With NMS and ensemble, we achieve about 70.9 performance in validation set. This figure shows the roadmap of our experiments with spares and resource. Okay, we also try IOUNet and soft NMS. IOUNet can also address the overconfident problem, but it will bring extra GPU memory cost. So we do not adopt it in our final submission. As for NMS, we found soft NMS also yield similar results to NMS and bounding box voting, but it's inefficient with numerous predictions. Then we introduce other tricks we do not make it work in our experiments. These tricks are actually validated in other competition and datasets, such as CUHK and ImageNet VID. First, we try to use deeper backbones, such as ResNet 101 and ResNet 152. Deeper backbone achieves not significant performance improvement for vehicle and pedestrian, but significant performance drop for cyclists. Similar observation is also found in our experiments with deformer-conv V2. We consider that this is because of the large recipe field and overfitting, but we do not have time to do more application studies. And the second is sequential NMS and video detection. We adopt an online setting by only use past frames, and we get marginal performance improvement for vehicle. We found that our model is hard to distinguish pedestrian and cyclist, so we try an additional RCN for better classification. Unfortunately, we do not make it work in our experiments. Okay, and here are our final submission results. Our method is RWTS-STAT, and we achieve about 74.4 MAP on the testing set, which is about 4 points better than the horizontal DAT and SP NAS. Thank you.
Thank you very much. Unfortunately, we won't have time for live questions, but please do ask your questions on Slack. Next up is Linlu from Berkeley to present on their results in the Waymo Open Dataset Challenge.
Yeah, hello everyone. My name is Linlu, so I'm glad to present my methods to the object checking. So this is the drawing work with Jiang Miao, Hao Feng, and Dr. Fisher Yu. Oops. So here is the outline of my presentation. I'll briefly talk about the motivation of our methods and move on to some discussion of our method QD track. I'll finally show you some results and visualizations. So first of all, let's talk about the motivations of our approach. So the current multiple object tracking methods will mainly follow the tracking by detection paradigm. So basically they will do detection in each frame and try to use some association algorithms to associate the objects. So the common associated algorithm like Hungarian algorithm will be used in this process. And most of them will use spatial proximity as a strong prior to associate the objects. So by saying spatial proximity, it can be intersection of union, IOU, or center distance. Some methods will also use some motion prior like common filter, optical flow, or bounding box regression, try to make the spatial proximity more accurate during the association process. However, the location heuristics only works well under simple scenarios. So if the objects are occluded or when they are under clouded scenes, it may easily lead to mistakes. And the search region is usually constrained to a local neighborhood. So making a strong assumption that the object will have like small movement between two frames. Meanwhile, the object appearance similarity usually take a secondary role. So people usually just use it as the supplementary in addition to the spatial proximity and use it to re-identify those vanished objects. But we are thinking about it from a different perspective. We think if we can learn instance representation properly, we can only use a simple nearest neighbor search in the embedding space. And that can help us to associate and distinguish our instances without any location and motion prior. But the problem is how to learn a good object representation. So previous methods will learn instant representations while sparse ground truth matching. So as you can see in this figure, basically they will take the ground truths from a pair of images and try to learn representation from them. The limitation of these methods is they treat it as a post-hostage after object detection. And they only use the sparse ground truth matching, but ignore 100 of the proposals on this image. In this way, it will only provide you limited supervision. So instead, we consider learning in addition to the sparse ground truth, but quasi-dense sample. So by saying quasi-dense sample, we include the 100 of regional proposal on these images. The benefits of our methods is it will be able to cover most of the informative regions on the image and will provide us more bounding boxes example and matching targets. So for the proposal that close to the ground truth boxes, it can serve as a positive example. And for those boxes in the background, it can be served as a negative example. In this way, it will provide us a valuable supervision so that we can learn from multi-positive contrastive learning. So next, I'm gonna introduce our method QD track, which is based on quasi-dense matching. It basically consists of 3 parts: object detection, instant similarity learning, and object association. So for the object detection part, we basically follow the common practice for modern checker or detector. So in our case, we use faster RCN along with FPN. So we'll have a pair of images and we will extract the feature maps and use bounding box head to predict classification and regression. But for the instant similarity part, we add an additional embedding head in parallel to the bounding box head. The embedding head will be used to extract embedding for the instance, and we use them we learn that well quasi-dense matching and contrastive learning. So that's the part of instant similarity learning part. So let's take a close look at our training objective. So for the embedding part, we will train our embedding while multi-positive contrastive learning. So similar to standard contrastive learning, we'll use a positive example and negative example in this loss function. We also add a auxiliary loss, which is the cosine similarity to constrain our cosine similarity. So for the C matrix here, it will be 1 if 2 examples are each other's positive example and 0 otherwise. We will train our model under the total loss here, which is consists of detection loss, embedding loss, and auxiliary loss. So our model is optimized end-to-end with joint detection and checking, and it's really a simple pipeline. Next, I'm gonna introduce our testing pipeline. So our testing pipeline is similar to our training pipeline. So you can see we will have a bunch of previous frames we serve as our memo, and we will have a current frame we want to take advantage and associate objects. We will have an embedding extractor to extract embedding for the bounding boxes in the current frame and previous frame. So for the current frame, we will get the embedding of all detection boxes. So for the previous frame, we will have 3 kinds of boxes embedding here. The first one is checklets. It's basically the checklist from the last frame. The second one is vanish checklets. That will refer to the vanish checklet where we need to re-identify the identity of the objects. The third one is what we call backdrop. So backdrop is actually the detection from previous frame, but they don't have high enough detection score and they don't match to any object. So different from previous method, just discarding those part of information, we save them in our feature space during matching. So during matching, we will use bidirectional softmax to match the current detection results to previous instances. So by saying bidirectional softmax, we mean we have a feature embedding and we will take the softmax around 2 directions and use the average of the softmax as our similarity matrix. This will naturally satisfy bidirectional consistency. So if you see in this case, if an object and that object is the nearest neighbor for each other, it will naturally have a high similarity score because they satisfy bidirectional consistency. Meanwhile, it can naturally handle the case where an object disappears and a new object appears because they will not satisfy the bidirectional consistency, thus we will have a low similarity score during the matching process. So in this way, it will help us to associate our object in a more robust way. Let's take a close look of the object association part. So as I said, in the current frame, we will have a bunch of detection boxes. And we associate them well bidirectional softmax to the tracklets and vanish tracklets and the backdrop. So for those objects that does not match to anything, but still have a high detection score, we'll just start a new tracklet for them. So finally, let's take a look at our result onto the object tracking benchmark. So we're able to achieve the second place onto the object tracking benchmark. And we have the #1 Mota L1 L51, and we are #2 Mota L2, but we are fairly close to the #1. And we want to point out that we don't use any special tricks during training and tracking. And we don't use any kind of location and motion information during the whole tracking process. It's purely based on the instant embeddings. So finally, I want to briefly show you some visualization of our results. So this is our results for our model from the Waymo 2D tracking dataset. And we use 5 cameras here, just want to give you an idea about the performance of our methods. Also, while we're working on this visualization, I want to briefly conclude my presentation. So we present a simple but effective tracker we call QD-Track based on the quasi-dense matching as I introduced before. So instead of just learning from sparse ground truths, we learn our instance representation from hundreds of proposals on the pair of image. So in this way, in the resulting feature space, we can simply just apply a nearest neighbor search, and it will effectively associate and distinguish objects without using any bells and whistle, and we don't use any location and motion heuristics. So in this way, we really simplify our training and tracking pipeline. So we also include more detail and experiments in the paper we published on arXiv. So if you are interested to know more, check out our paper on arXiv and check out our GitHub page. And that's the end of my presentation. Thank you.
Thank you for the great presentation. Please ask your questions on Slack. Next up is Feng Wang from TuSimple.
Okay, good morning, everyone. Thanks to the Waymo team to give me a chance to give a presentation about our solution on the 3D object detection. I'm Feng Wang from TuSimple. Okay, here is the whole architecture of our solution. It includes a bottom feature representation module, a fast RCN-like module, and a point net refinement module. First, we split the space into voxels and concrete the bins on height to build BV features. Then the features are fed into a 2-stage fast RCN-like detector. The difference is that in 3D detection, the bounding boxes are rotated ones. So we do add extra regression target on the RPN and do the rotated ROI align in the RCN and to get the refined bounding box. Then we do another stage of refinement by using the point pooling operation to pull the original points and use a point net to refine the bounding box further. Okay. Today, I don't want to get to the details of our whole architecture. I just want to talk about some interesting tricks we found during the competition. Firstly, is about the bottom feature representation. Our work is based on point pillars. Point pillars is a very effective feature representation. It splits the space into pillars with no division on the z-axis. The points in each pillar is included by a point net. Note that this is only a one layer. point net. However, we find that the representation power is quite limited. The weight and bias of one fully collected layer can be seen as multiple lines. So this is 2 lines, and each point will be projected on the lines to get the feature. Through the max pooling operation, only the max values could be preserved. So look at this point. You can never find a line to make this point to be selected. So if there is some potential structure inside the pillar, the one layer point net could not represent it. So our solution is quite simple. First is simply add one more layer, so to build a 2-layer point net. Then the point net will be able to extract much more complex structures. Second, we split the z-axis into multiple bins. And thanks to the dynamic voxelization, which is a work from Waymo, there is actually no extra cost when we split the pillars into multiple bins. So this improvement is almost free. Then let's talk about the point RCN refinement. It was originally proposed in point RCN, which from Shaoshuai, who present before. It used a point pooling operation to pull the original points, and then the points are fed into a point net to get the refined bounding box and a new confidence score. But during the implementation, we found that the classification accuracy is not very good. Then we dig into this problem and find that there is an ambiguity problem on the classification target of point RCN. Let's see the example. The red bounding box is the ground truth, and the green dashed bounding box is a good prediction. And the blue bounding box is enlarged from the green one, but it has much lower IOU score with the ground truth. But as you can see, the green and the blue proposals actually put the very same points. So the RCN model just don't know what's the size of the proposal. So we add virtual points into the polled points to let the RCN know how big the proposal is. Then the RCN maybe know that around this virtual points, there is no real points in its neighborhood. So it will know, oh, this proposal is too big, and we should give it low confidence. And finally, this is a trick on the data augmentation. We found that the amount of cyclists in Waymo open dataset is not as many as vehicles and pedestrians. So we randomly sample cyclists from a database. Then we do one step after the insertion. Note that the newly added objects, this cyclist, will occlude the points behind them. So we simulate this feature. Please also look at this pedestrian. It will be occluded by this newly inserted cyclist, and this object is also need to be removed. Okay, this is our ablation study. We found that the 3D voxel improves performance very significantly, and it's almost free. And the cyclist sampling also very effective. It improves cyclist score for more than 10 points. And the point RCN module also improves the bounding box by about 5 points. Yeah, so this is our whole solution. Thank you.